Okay, terminal velocity part 2. We talked in part 1 about this skydiver or man jumping out of a plane having a weight of 700 newtons. That's the force that this man has, 700 newtons of weight. He jumps out the plane and immediately some air hits the man. We call that air resistance. Now let's say about 150 newtons of air resistance force is acting on the man. He speeds up, he accelerates because there's not enough air resistance to stop him accelerating, so he speeds up and up. And as he speeds up and up and up and up, more and more and more and more air hits the man. So his air resistance increases. So it's gradually going up from 150 to eventually resting at 700. It doesn't go higher than 700. At this point, it's now nicely balanced. We have no resultant force, okay? But knowing that the man was moving in the first place must mean that this man here has a constant speed. And we call that constant speed terminal velocity. So great, now what does he do? He opens his parachute. Now, if he opens his parachute now, you've still got the weight of 700 newtons that hasn't changed because he was carrying it on his back. But all of a sudden there is loads and loads of air hitting the man. At this point there was 700 newtons, remember, because he's going such a speed. And now there's even more because he's opened this parachute. Let's say 1,000 newtons of air resistance. Now this diagram doesn't mean that the man is going upwards. Please, no, he does not go upwards. He doesn't go upwards because he's already moving at a constant speed. The air resistance begins to slow him down. He decelerates and slows down because there is more air resistance than there is weight. Okay, he does not float upwards. No, okay. All right, that's the same as the car one, if you've seen the car one. So he is slowing down. Now, because he slows down, less air hits him because he is slowing down. Because less air hits him, this air resistance reduces until finally they balance out again at a second terminal velocity. Okay, and at this terminal velocity is going slower. He can then put his feet on the floor quite happily without ending up a squashy mess on the floor. Now you'll get a graph like this, maybe. Let's go through it. So here he is, he's jumping at the plane. There he is there, the 700 newtons here. Okay, so this one is here. He is gradually accelerating, okay, accelerating as more and more air hits him until the amount of air resistance and his weight balance out. That's it here. So he's going at a constant speed here, 40 meters per second. His parachute then opens, and here it is here, so he's 700 newtons down, but now we've got a higher air resistance up here. So he doesn't go upwards, remember, he slows down. So here's the parachute opening, and he's decelerating rapidly. And because he decelerates, less air hits him, which is here, 700 newtons. Okay, so he reaches a final terminal velocity, a final speed, until he gradually then drops to the floor. At the floor, he's got 700 newtons down and 700 newtons force upwards. That's otherwise he would sink into the ground. Okay, so these different stages. 700 newtons of weight, more and more air hits him, he goes faster, 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 faster. Eventually the forces balance out. No resultant force, therefore he's going at a constant speed. And in this case, it's his top speed, so it's his terminal velocity. His parachute opens, increasing the air resistance, slowing the man down. And if he slows down here, then the air resistance also decreases. He then reaches a final terminal velocity, which is here, where the forces are balanced again. He then can land on the floor. It would be the same if it was a bicycle or a car, etc. It would accelerate, it would reach its terminal velocity, but at this point then that would be it. It would be reaching its terminal velocity. Okay, so hopefully that solves that. There you go.